Section 3.4 is about applications on decay. So the equation dp over dt equals negative kp, where k is greater than 0, shows p to be decreasing as a function of time, and the solution is p of t equals p naught e to the negative kt. And this shows it to be decreasing exponentially. This is exponential decay. The amount present at time t is p naught. And so you can see between the two graphs below, a growth is going to continue to increase, whereas the decay, which is what we're considering, is going to get smaller and smaller, almost to 0. So radioactive elements decay exponentially. That is, they disintegrate at a rate that is proportional to the amount present. So let's start with example 1. Strontium-90 has a decay rate of 2.8% per year. The rate of change of an amount N of this radioactive isotope is given by dN over dt equals negative 0.028 N. We want to find a function that satisfies the equation. Let N naught represent the amount present at t equals 0. So N naught is that initial amount. But we know that when we have this differential, the derivative in this equation, we have a function for N. And that's N of t equals, we have our N naught, which we don't know how much we had, e raised to that negative 0.028 times t. So now that we have this idea of the formula, we can plug in different values for t or N naught or N of t. So for part B, we're going to suppose that 1,000 grams is present at t equals 0, which means that is the beginning amount. So we know that N of t equals 1,000 e to the negative 0.028 t. We want to know how much is going to remain after 70 years. So we're given t equals 70. So we're going to find N of 70, which is 1,000 e to the negative 0.28 times 70, or we've got 1,000 e to the negative 1.96, and that's 1,000 times approximately 0.14085, 84209. And so we get that N of 70, there would be approximately 140.9 grams left after those 70 years. Now we want to know how long will half of the 1,000 grams remain. So that means we want to know how much time it takes for the 1,000 grams to get to 500 grams. So this time N of t is 500 equals 1,000 e to the negative 0.028 t. We want to solve for t. So we're going to divide by 1,000 on both sides. And so the thousands cancel, and we get 1/2 equals e to the negative 0.028 t. To get the t out of the exponent, we need to take the ln of both sides. So we're going to take the ln of 1/2 equals the ln of e to the negative 0.028 t. So we have ln of 1/2 equals, the ln and the e essentially cancel, and we're left with just the exponent. And then our last step is to divide by negative 0.028. So we get t by itself. And we get about 25. Theorem 10 says the decay rate K and the half-life T are related by, we have two formulas. K equals ln of 2 over T, or T is equal to ln of 2 over K. So we can find the decay rate or we can find the half-life by using the other variable. So plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about 0.028% per year. What is its half-life? So we're looking for the T, capital T. So we're going to use the formula. T equals ln of 2 over K. And we know the K this time is 0.028%, but we want to make sure that we plug in a decimal. So we need to move that 2 spots to the left. So we've got 4 zeros. With a 28. And that gives us about 24,755 years. And just so you can see it on the side. We want to move this decimal 1, 2 spots. For example number 2, plutonium-239, a common product of a functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about 0.028% per year. What is its half-life? So we're looking for capital T. So we have T equals ln of 2 over K. Well, our K was given in percentage. We need to make sure we convert this to decimal before we plug it into the formula. So we're just going to move this 2 spots to the left and then plug it in. So we have ln of 2 over 0. We got 3 zeros and then 28. And that gives us approximately 2,475 years. The radioactive element carbon-14 has a half-life of 5,730 years. The percentage of carbon-14 present in the remains of plants and animals can be used to determine age. Archaeologists found that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? So first what we have to do is we need to find the decay rate. So we need to find K. Well, we have a formula for that. K equals ln of 2 over T. And T is the half-life. Well, our half-life is 5,730. And so we get about 0.0001297. So we need to substitute this into our formula for decay. That is n of t equals n naught e to the negative kt. Well, we've got k, so let's go ahead and plug that in. So the rest of it says that it had lost 22.3% of its carbon-14. Which means how much of it remains. So from 100%, if we lost 22.3, that will leave us with 77.7% remaining. Or that would be 0.777. So that's the ending part. We need to find t. So it doesn't matter if we have an initial amount, we can always just use n naught as our variable. So because we're looking for 77.7% of the original, n of t is now going to become that 0.777 times n naught, because it's of the original, equal to n naught e to the negative 0.0012097t. And we are solving for t. So what we're going to do is we're going to divide both sides by n naught. And so what ends up happening is the n naughts cancel on top and bottom. And we're left with 0.777 equals e to the negative 0.0001297t. Just like with the other problems, we need to get the t out of the exponent. So we're going to take the ln of both sides. And so on the left-hand side, the right-hand side, the ln and the e end up canceling. And so we're just left with the exponent. And then we want to divide both sides by that long decimal. And that will give us t. And so we end up getting about 2086 years old for t. How old is a skeleton found at an archaeological site if tests show that it has lost 60% of its carbon-14? So this is very similar to the one we just found. So we need to find K first. We need to know what the decay rate is. And so K is ln of 2 over T. From the previous example, we know that carbon-14 has a half-life of 5,730 years. And so again, we have that long decimal, 0.0001297. And so I'm going to plug that into our formula. This time it had lost 60%, which means that there is 40% remaining, or 0.4 of the original. So just like in the last example, we have 0.4 of the original amount, which we don't know, equal to n naught e to the negative 0.000120970. From here, these work the exact same way. So we're going to divide both sides by n naught. So they cancel on the top and bottom on both sides. We have 0.4 equals e to the negative 0.000120970. And then we want to go ahead and take the ln of both sides so we can get the t out of the exponent. So we get ln of 0.4 equals negative 0.000120970, and we want to divide by that long decimal again. So they'll cancel on the right. And we end up getting about 7,575 years old for t. Now let's look at some business applications. So following the birth of their granddaughter, two grandparents want to make an initial investment of P naught that will grow to $10,000 by their child's 20th birthday. Interest is compounded continuously at 6%. What should the initial investment be? So continuous compounding is given by P of t equals P naught e to the kt. We want to know what P naught is. We know that the end goal, which is P of t, is $10,000. We know that the interest is 6%, so K is 0.06 and T is 20 because they want it to wait till their 20th birthday. And so we have 10,000 equals P naught e to the 0.06 times 20, which is 1.2. I'm going to divide both sides by e to the 1.2 to get P naught by itself. So on the right hand side it cancels. And we end up getting $3,011.94. That is what their initial investment would need to be to make sure that their grandchild would have $10,000 on their 20th birthday. We're going to repeat the exact same thing, but with an interest rate of 4%. So it's going to be very, very similar. P of t equals P naught e to the kt. We still want it to grow to $10,000. I'm looking for that initial, but now I have an interest rate of 0.04 instead of 0.06 times 20. Well, that's just 10,000 equals P naught e to the 0.8. And then we're going to divide both sides by e to the 0.8. And we end up getting $4,493.29 for P naught. So because the interest rate is lower, we have to invest more initially. Theorem 11 says the present value P naught of an amount P due T years later at an interest rate key is compounded continuously is given by P naught equals P e to the negative kt. So instead of going the way that we just did, they're just giving you the formula to find the present value. You can still do what we did for the last two examples and get the same answer. Next thing is Newton's law of cooling. So the temperature T of a cooling object drops at a rate that is proportional to the difference T minus C, where C is the constant temperature of the surrounding medium. Thus, dt over dt equals negative k times T minus C, and this function satisfies T equals T of T equals A e to the negative kt plus C. So using that information, let's try example number 7. A body is found slumped over a desk in a study. A coroner arrives at noon, immediately takes the temperature of the body, and finds it to be 94.6 degrees. She waits 1 hour, takes the temperature again, and finds it to be 93.4. She also notes that the temperature of the room is 70 degrees. When was the murder committed? So we're going to assume that the normal temperature of a body is 98.6 when it was committed, just to make things easier. So let's assume that the person who was murdered had a normal body temperature, like they weren't sick or anything, of 98.6, and that was at T equals 0 as soon as the murder was committed. So we can find our formula. We have T equals A e to the negative kt plus C. Well, our starting temperature was 98.6 equals A e to the negative k. Little t was 0 because it's right when the murder happened, plus 70 degrees because that's how much or how cold the room was. And so that means we have 98.6 equals A e to the 0 plus 70. Let's subtract 70 from both sides. That's 28.6. And e to the 0 is just 1, so we get A. So now that we have A, we can figure out the formula a little bit more. So plugging back into the original, that's 28.6 e to the negative kt plus 70. we need to find how many hours since the murder was committed, but we need to find K first. So we have two temperature readings from the coroner. We have that it was 94.6 when they arrived at noon, and then we also have that it was 93.4 an hour later. So let's go ahead and solve this information. So we have that it was 94.6, which is equal to 28.6 e to the negative k, and I'm going to say n for noon, plus 70. And so we can simplify this one a little bit. Let's subtract 70 from both sides. That's 24.6 equals 28.6 e to the negative kn. And we also have that the temperature was 93.4 degrees, but this was 1 hour after the original. And so that's n plus 1. So again, let's subtract 70. We've got 23.4 equals 28.6 e to the negative k times n plus 1. And so now we can solve for k. We're going to set up a proportion. So 24.6 over 23.4 equals, and on the top we'll have 28.6 e to the negative kn, and on the bottom we'll have 28.6 e to the negative k n plus 1. While on the right hand side, the 28.6 ends up canceling. So we end up having 24.6 over 23.4 equals e to the negative kn over e to the negative k n plus 1. I'm going to simplify the right-hand side a little bit using those rules that we learned from a previous chapter. So that's e to the negative kn, and then we have minus negative kn and negative k. So I just distributed the negative k on the bottom to both pieces, and then when we bring it to the top we end up subtracting. So this actually simplifies to something nicer. That's 24.6 over 23.4 equals e to the negative kn plus kn plus k. And so the negative kn and the kn cancel. We've got 24.6 over 23.4 equals e to the k. And so to find k, we're just going to take the ln of both sides. So ln of 24.6 over 23.4 equals k, and that's approximately 0.05. And so now we can plug it back into one of the original equations we set up here, either this left one or the right one. I'm going to pick the left one so that we can find n, which is the time of the murder. So we have 24.6 equals 28.6 e to the negative 0.05 n. And so solving, we're going to divide by 28.6 on both sides. So 24.6 over 28.6 equals e to the negative 0.05 n. And then we're going to take the ln of both sides so that we can get the n down. So we have negative 0.05 n. And the last step is to divide by 0.05 on both sides. And so you get that n is about 3.